In the previous lecture, we have introduced the continuous conduction mode of switch mode converters. We call it CCM. In CCM, we can have two operation modes in one switching cycle. We usually define as mode 1 and mode 2. When we utilize the unidirectional power semiconductor devices, the DC-DC converter might enter into a new conduction mode, which is discontinuous conduction mode. We call this as DCM mode. So in this lecture, we will introduce the DCM operation mode. So discontinuous conduction mode. So first, let's see when the DCM could happen. So DCM typically occurs with large inductor current ripple. In a converter operating at light load. And containing unidirectional switches. Current unidirectional switches. So basically, there are three keywords here. One is the large inductor current ripple. Secondly is the light load. The DCM usually occurs at light load. And thirdly, there is a condition which is current unidirectional switches. So next, we'll try to analyze the DCM operation quantitatively. Before we make the mathematical analysis, we first introduce what is current unidirectional switch. So there is an important concept, which is the quadrant. So the quadrant is closely related to the current unidirectional switches. So first, let's see what is the quadrant. So suppose we have a switch. We use the switch model to describe the switch. So there are two quantities. One is the off-state voltage. We use V to denote it. And second one is the on-state current. When the switch is conducting, how would the current flow? Based on those two quantities, we can plot a plane, 2D plane. So the x-axis, we specify it as the off-state voltage. And the y-axis, we specify it as the on current. Determined by the polarity of the on-state voltage and off-state voltage and on-state current, we can have four quadrants. So here's the quadrant 1, quadrant 2, quadrant 3, and quadrant 4. So next, we can put different switches into this quadrant and see what quadrant properties does the switch have. So first, we look at the most fundamental switch, which is the single quadrant switch. Single quadrant switch means that on-state current and off-state voltage can only occur in one specific quadrant. For example, the most classic single quadrant switch is a diode. If we plot the quadrant feature of the diode, so here is voltage, here is current. We can see that the diode quadrant can only exist like the on-state current will be unidirectional, right? This is because diode can only pass unidirectional current. And in the off-state, diode can only block the reverse bias. So after we plot the quadrant behavior of diode, we can see that diode is a single quadrant switch which have its conduction in quadrant 2. Right? Another important single quadrant switch is IGBT. So for the IGBT, we can also plot its quadrant feature. Current, voltage. Remember, in the last lecture, we mentioned that in the off state, the IGBT can only block forward bias, and its reverse blocking capability is very weak. So the V feature will be existing like this. In the reverse mode, the IGBT will be easily destroyed. And for the current, the IGBT can only pass unidirectional current. So it is a quadrant 1 switch. Next, let's look at the 2-quadrant switch. The most commonly seen 2-quadrant switch is the power MOSFET. So this is a power MOSFET. As we discussed in the last lecture, there is a parasitic body diode in this power MOSFET. So we can plot its quadrant plane correspondingly. So here is the off-state voltage, here is on-state current. The polarities are defined as here, right? So when the MOSFET is off, the device can only block the forward bias, because for the reverse parts, there is a diode which will pass the current. So the V feature will be only positive. And when the MOSFET is on, the channel will be conducting. So the channel can pass bidirectional current. So the current will exist both in positive and negative axis. So this clearly indicates the power MOSFET is a 2-quadrant switch with quadrant 1 and quadrant 4. So we call this as current bidirectional. switch. And second one will be IGBT in series with a diode. So here's IGBT. Suppose we plot a diode in series with IGBT. Remember, we mentioned that IGBT has weak reverse blocking ability. So that's why we place a diode in series with it. So the diode can help to block the reverse voltage. Then we can plot its IV feature correspondingly. So for the blocking capability, since we have the series diode, so the IGBT series with diode can block voltage bidirectionally. In the forward direction, if the IGBT is off, itself can block the forward bias. In the reverse direction, if IGBT is off, this series diode will block. So we have the voltage bidirectional feature. For the current, in the on state, the current will only pass this way. So IGBT series with diode will also have quadrant 1 and 2 feature. So it is a 2-quadrant switch. And the third category will be the 4-quadrant switch. You might be curious, can we have a single device which can have this quadrant switch behavior? For semiconductor device, the answer is no. We have to have multiple devices working together to achieve this target. For example, we can have 2 MOSFETs. So this is a MOSFET 1. This is MOSFET 2. Both MOSFET 1 and MOSFET 2, they are NMOS, but they are back-to-back connected. So their body diodes are also back-to-back. So for such a device, if we plot the IV feature, we can see that in the off state, if both channels are off, this switch will be equivalent to 2 diodes back-to-back, so they can block voltage bidirectionally. And if both channels are turned on, so we can pass current also bidirectionally. So that is one typical example. And we can also use IGBT to achieve this target by combining 2 IGBT series with diode. So here's one unit, and we can have another unit in parallel. So this parallel structure can also realize the 4-quadrant feature. Like in the on state, so this branch passes current in this direction. And this branch passes current in the other direction. In off state, both can block voltage bidirectionally. so which realized a 4-quadrant switch. So different type of switch have different applications in power electronics. So if we go back, we can see that here is the current unidirectional switch. So this means that we typically should have the diode, or like this one, in the DCM operation modes. In this subsection, we have divided the semiconductor devices into multiple categories, mainly based on the on-state current and off-state voltage. So we can see that we can divide the devices into single quadrant switch, 2-quadrant switch, and 4-quadrant switch.